Hey everyone, how's it going? Have you ever stood outside and looked up into the sky and ever thought, is anyone watching me from a different planet? Sometimes I ponder this kind of question a lot, just because of the vastness of space, and I always tend to wonder if life does exist on other planets, what kind of planets these extraterrestrial beings would live on, and how these kinds of planets will support life. It's always interesting to think about this kind of thing, just because I genuinely think that life does exist elsewhere in the universe, and I think there is millions of extraterrestrial beings or extraterrestrial life that exists, and we simply aren't alone. So today I did a podcast with Professor Suzanne Aigrain, who essentially finds exoplanets using telescopes. And she analyzes the data and tries to figure out the composition of the atmospheres, and whether perhaps not these atmospheres are similar to Earth, and whether these atmospheres can actually potentially hold the right conditions for extraterrestrial life. And it also gives us good information on how the Earth might have formed and how life began here. So sit back, relax, and I hope you all guys enjoy the podcast today. Okay.
Alright.
And we're recording. Just going to turn my phone on silent.
I should do the same. Okay.
Hi everyone, welcome to the Frontier of Knowledge podcast. Today I'm joined by Suzanne Aigrain. Is that how you pronounce it? Okay. If you want to give the listeners a bit of background information on yourself and tell us what you do exactly.
Okay, so I'm a professor of astrophysics here at the University of Oxford, and I work on exoplanets, which are planets which orbit other stars than the Sun. So I look for them, I try to detect them in big surveys, and I try and study them both in detail, looking at individual planets, trying to understand what they're made of, what's in their atmosphere, whether there might be suitable place for life to develop, and then also looking at the population as a whole, trying to understand how frequent different kinds of planets are, how diverse planets in the universe are. And a lot of what I do is about data analysis, so it's about finding tiny signals in noisy data.
You have an awesome job, by the way.
I'm very lucky.
That's a really amazing job. When I was a kid, I was thinking, that'd be a really good job to have, just kind of look through telescopes and trying to find planets outside the solar system. So that's amazing.
Well, it's really it was really forward thinking that you thought about planets outside the solar system when you were a kid, because, well, I suppose you were a kid not that long ago, but it's a fairly new field. So when I was a kid, nobody thought about looking for exoplanets, but most people didn't think they even existed. So.
Really? Wow, it's quite amazing. I think when I was 14, my parents got me a telescope, and I peered through the telescope on a clear night, when I could find a clear night, and just looked into the moon. I could see all the craters on it. If I got a really decent eye, I could sometimes see Jupiter. And it was actually amazing how powerful the telescope was. It was just a really small one.
Yeah, it's true. You can see a lot with a small telescope. And in fact, one of the things that attracted me to this area of astrophysics when I first started is the fact that you can actually find planets around other stars using quite small telescopes.
Wow, okay.
So the first, so the method I work on is mainly is called the transit method. When a planet passes in front of the star, it orbits, and so it blocks out the part of the star.
Okay.
Now we can't resolve that, but what we see is the star becoming slightly dimmer for a short while.
Okay.
And the first planet that was found to transit was found in 2000 using a tiny telescope with a 5 centimeter aperture.
Wow.
And by a graduate student working from a parking lot in Boulder, Colorado. So it's quite a nice story. And since then, lots more small aperture telescopes have made big contributions to the field. And there's amateur astronomers looking at transiting planets every night all around the world. So
it's amazing. Well, there are a lot of exoplanets to be found, to be honest. I mean, it's really cool. So what kind of telescopes do you use exactly? Do you ever use a Hubble telescope, or do you?
I have used a Hubble telescope before. So I mainly work with space telescopes, first of all, because A lot of what I do requires having very precise data, measurements of the brightness of stars over a long period of time.
Okay.
And the atmosphere blurs the lights from the star and it makes them scintillate, it makes them twinkle,
Okay,
little
yeah.
star. And that's bad for the kind of science I'm trying to do.
Okay.
So getting above the atmosphere solves that problem. And it also means that you don't have to interrupt your observations every day or every time the weather's bad.
Okay.
And in fact, if you put your telescope not in orbit around the Earth, but somewhere else,
Yep.
then you can actually look continuously at a given part of the sky without stopping for years at a time, potentially. So that's why we use a lot of space data.
Yep.
And we use, so there are dedicated space telescopes that were launched in the last few years to look for transiting planets. The first one I worked on was called Corot. It was a French-led mission. It stands for convection, rotation and transits. It also looked at seismology of stars, so trying to understand the interiors of stars by looking at how they pulsate.
That's really cool.
It's really cool as well. So that could be a subject of a whole other podcast. And then more recently there was the Kepler mission, which you may have heard of. That was an American-led mission, but I also worked a bit on that. And once we find transits in the data returned by these missions. We also find transits in data from ground-based telescopes. So I was briefly involved in one of the most successful ever. It's a British project called the SuperWASP project.
Oh yeah, I've heard of that.
And once we have transiting planets, particularly if they orbit bright stars, then we can also try and look at their atmosphere. And we do this, one of the main ways we do this is by looking at, so if the planet is passing in front of the star, then there's a little ring of atmosphere around the planet that the light of the star will filter through.
Okay.
And whatever gases are in the atmosphere of the planets will absorb some of the light. So if you compare the light you get when there's no planet and the light you get when the planet is there, you'll see tiny differences, and they really are tiny. They're like 1 part in 10,000, even in the best cases. Then you can tell what gases are in the atmosphere, you can tell if there's clouds, if there's hazes. And to do that sort of thing, we use, amongst others, the Hubble Space Telescope. And we're also very excited by the James Webb Space Telescope that will launch. And then,
that's going to be something else.
That's going to be very, very powerful.
Isn't it 3 times the size of Hubble at the moment?
So the diameter of the telescope is 6.5 meters, whereas the diameter of Hubble is 2.5 or 2.4. So it's going to be a really, really powerful tool. And another thing that Hubble started, but James Webb will be able to do even more. And there are also some really cool instruments on the ground doing that with the Very Large Telescope. In Chile, is to look for planets directly, so to try and just block out the light of the star and look for tiny little pinpricks of light next to the star.
See little green men running around the planets. That would be amazing.
A little bit ambitious. We're still talking about the whole planet in 1 pixel, right? But so James Webb will have instruments equipped with coronagraphs, and there's instruments on the Very Large Telescope. There's an instrument called Sphere, and there's a few other instruments around the world that are doing that work right now, and are getting really nice results. It's not the area I work in, but it's really exciting.
That is really cool, though. One of the great things I love about telescope, especially Hubble, is on my computer I have all the images. Well, a lot of the images it's taken over the years of different nebulae and different kinds of stars, different galaxies, and it's just amazing.
These images are amazing. Unfortunately, in the field of exoplanets, we rarely get pretty pictures. I mean, usually you just get a picture of a field full of stars, and if you're looking with Hubble, if you're doing the experiment I described with trying to see the light filtered through the atmosphere, you take a spectrum. So you actually take the light of the star and you disperse it, you spread it according to wavelengths. So what you get is a great big smudge. It doesn't look pretty at all.
But at least when you interpret the data, you kind of know then what kind of planet, what kind of gases and kind of atmosphere you're looking at. Then you have a rough idea. Already when we see the transits, from the transit we get the size of the planet relative to the star, right? The depth is the ratio of the areas between the star and the planet. And then if we can also measure, do you know the Doppler wobble? Yes.
So if you can also measure that, then you get the mass of the planet relative to the star. And then if you know enough about your star, which generally speaking you do, you can get the mass of the star and the size of the star, and so then you get the mass and the size of the planet. And so from that alone you can work out roughly what it's made of, so you can tell whether it's a giant planet made mainly of gas like Jupiter, or whether it's more of a terrestrial planet. And actually one of the really exciting things is that there are lots of planets that are in between that have no equivalent in our solar system, but they're actually the most common planets we found elsewhere. We call them super Earths or Neptunes, and they have masses between say 4 and 20 times the mass of the Earth. And they could be made up of lots of different things. They could be mostly rock with a tiny bit of gas. They could be almost all water. There could be things we haven't thought of yet. And by looking their atmospheres, we can also look, what goes on with those planets.
That's
They're quite
amazing.
exciting.
I want to talk about quickly is it TEPPIST one? The system?
TRAPPIST one
system, yes. So when I first heard the story of what happened there, amazing, they found 7 planets circling a single star. I think it was a low energy dense star? Was it very
low mass
big?
star, very faint, yeah. So TRAPPIST is an experiment that specifically targets these very, very small stars.
Okay.
And it's sort of in the line of previous experiments that have... So initially, people were mainly looking for planets around stars like the Sun.
Okay.
Because the thinking is basically, first of all, those stars we understand very well, and there are many of them, and they're not too faint. And we know that at least one of them has planets, so there's good reason to think that others might. But over time, people have started to realize that if you go for a smaller star, the same planet will produce a bigger signal, because the signals that you get are relative to the size of the star.
Okay.
And so if you're looking, for example, for an Earth-like planet, it's easier to find it around a smaller star.
Okay.
The only problem is that these small stars are fainter, and they emit their light in the redder part of the spectrum.
Okay.
So you need instruments that are capable of detecting that red light and measuring it very precisely.
Kind of infrared kind of...
Yeah, infrared cameras, or at least near-infrared cameras. And over time, people have... So there was one experiment, the first experiment to specifically target these low-mass stars called M stars, was called MERTH. Run from Harvard in the United States, and they found a couple of planets. They found 3 now, but they're around 3 different stars, I should say. And their results, and also results from the Kepler space telescopes, which did observe some of these low mass stars, suggest that small-ish planets up to say 4 times the size of the Earth, are actually very common around these small stars. Before that, a few people had looked and found that big planets like Jupiter were quite rare around these small stars, but small-ish planets seem to be very common. And so then the people who are running the TRAPPIST experiment, who's led by Michael Guillon from Liège, and his collaborators, they thought, well, let's go for even smaller stars that nobody has looked at yet. And those stars are literally the size of Jupiter. So they're very small. They're about 100 times more massive than Jupiter, but they're literally the size of Jupiter.
Oh, I see. So they're more mass, but in a smaller volume.
Yeah, because they're basically compressed by their own gravity. So although they have more mass, they end up in the same volume. And nobody knew whether we could extrapolate like that and say, well, if small stars have many small planets, then maybe even smaller stars will have more. But it seems this is very early days, but it seems that from what they found, they certainly can't be rare, because they've found a few already. But it's also very interesting that they found this system where they have 7 planets within, all of which orbit in less than 20 days.
That's amazing.
So it's a very compact system. And this is something that we have been finding in general with systems with multiple small planets in them, is that they are very compact. And it tells us something about how they form. So it's likely that there's a lot of gentle interaction between the planets as they form. That's the only way they could get into this compact kind of configuration. If they were interacting more violently, some of the planets will get ejected, and if they were not interacting at all, they wouldn't have got so compact. So that gives us some really interesting clues as to how planets form.
That's amazing. That's really cool that people like yourself are doing this kind of work. And
I mean, actually, I haven't done anything on TRAPPIST-1. I find it fascinating, but
I mean, just in general with this kind of field, it's amazing. And I think the more kind of invest in this kind of area of science, the more we're going to learn about how different planets form, and maybe learn something about how Earth was formed in a sense.
Of course, I mean, we're interested in how all planets form, but one of the big reasons is because we want to understand we want to put our own planet and system in context, basically.
That's amazing. So what kind of habitable, are these kinds of, do you think the planets on TRAPPIST-1 are going to be habitable, do you think, to a certain degree, or can we...
I think that's open to debate or scientific inquiry, because so there are 3 planets in the system that have temperatures nominally, so if you calculate what their average temperatures should be, based on how much light they receive from their star, that temperature should be between 0 and 100 degrees Celsius on average. Now that's a very approximate number, because we don't know what the atmosphere of these planets is like, and the atmosphere affects, obviously, you've got greenhouse effects and various other things. But the other thing is that these planets have very short period orbits, right? They have orbits of a few days.
Mm-hmm.
The reason that they are not scorching hot is because the star is so faint. Okay. But because they're so close to the star, they always show the same face to the star.
Oh, so they're tidally locked.
They're tidally locked, like the moon is compared to the Earth.
Mm-hmm.
And that means that they'll have one extremely hot day side, one extremely cool night side.
Okay.
And whether or not that makes for an inhabitable place is very... We really don't know, because we don't know enough about what they're made of to even start modelling them.
Okay.
But you could imagine circumstances where there's enough heat transported from... So probably where the light is received, it's far too hot.
Okay.
But it could be that if some of that heat is just transported a bit towards the night side, then you might get a region.
I see, like a medium.
Yeah, a temperate region. And the reason we think we need a temperate region is because for all the chemistry that supports life to happen, it needs to happen in some kind of solvent, and it's much easier if that solvent is liquid.
Okay. That makes sense.
Now, the other reason that people think that the planets around TRAPPIST-1 may not be habitable is because stars like TRAPPIST-1, especially early in their lives, emit a lot of UV radiation, ultraviolet radiation, and we don't know very much about what that does to complex molecules.
Okay.
It may actually be that it basically helps speed up some reactions, but it may also make it much more difficult for complex molecules to be stable.
Okay.
So it's hard to tell what that does. I've actually just asked a scientist from Cambridge to come and give us a talk on that because I don't understand it.
Oh, really?
I'd love to understand it.
That's awesome.
Yeah.
That's amazing. So from the planets that you've looked at, which ones do you think have you looked at the compositions of certain atmospheres as you think are going to be suitable for?
So we actually haven't been able to probe in detail the atmospheres of any planets that are in the habitable zone.
Okay.
So far, or that are habitable, because the technique that I described, the signal that you get is proportional to the thickness of the atmosphere squared.
Okay.
And of course, planets like the Earth have a very thin atmosphere compared to their size. So it's much more applicable to planets with a thick atmosphere of hydrogen and helium, like a gas giant planet or something like that. There are other ways to try and look at the atmosphere of a planet, and one of them is to directly image it, so separate the light from the star with a chronograph and then take a spectrum.
Okay.
But that requires a very big telescope.
Okay.
So it may be that James Webb can do it for some of these planets around low mass stars, provided we find enough good ones.
Okay.
There's a couple of planets that have been found recently that are good candidates for that. Otherwise, we will have to build an even bigger space telescope.
Which I think was probably going to happen in the next 10, 15 years or so.
Well, it probably won't. It probably will happen, but how long it will take, it depends on lots of factors outside our control, like who's president of the United States,
or who's going to invest in it.
Yeah, exactly. And so the point is that I was involved in a study where we looked at all the different trade-offs for how big would the telescope need to be and how powerful would the instruments need to be that you put on it. And the upshot is you would probably want something that would be something like 12 meters diameter, so twice as big as James Webb in space, with a very carefully designed chronograph, and then it could take spectra of Earth-like planets potentially, which would be really cool.
That'd be really cool. And then you model them on a computer, and then you kind of
basically what you do is you get a spectrum that just tells you how much the atmosphere emits light at different wavelengths.
Okay.
The atmosphere of the planet, and you model that using a theoretical model. So you say, oh well, let's imagine my atmosphere is made up of this, and that there's so much light filtering through these planets radiate in two ways. One of them is that they're warm, so they glow in the infrared, and then that infrared light filters through the atmosphere, is absorbed by certain things, reflected down by clouds, etc. And the other way in which they glow is by reflection, so they receive light from the star, and that some of that light is reflected back to space by either the planet's surface if it goes down to the surface, or the atmosphere at different altitudes if it has clouds, or if it has different things that reflect at different altitudes. So you've got light that filters down, some of it's reflected, some of it bounces back but is absorbed on the way out, etc. And so you can tell from your spectrum what is in the atmosphere of the planet. And there are certain combinations of molecules that are particularly telltale signs of biological activity. So, for example, if you see water vapor, carbon dioxide, and methane together, that normally these you wouldn't expect to see both carbon dioxide and methane in large quantities in the atmosphere. Or the other one that people have.
Why is that though?
Because normally all of the carbon will either be bound up with oxygen or bound up with hydrogen, but not one or the other. Especially if you've got then free oxygen, so if you've got oxygen or ozone in your atmosphere in large quantities, then it would normally react with the carbon.
Oh, I see.
And if you've got free oxygen and you've got some of these other molecules there, it's telling you that something's producing the oxygen, because oxygen is a very reactive molecule. It will not, if it finds something to bind with, it will.
Oh, I see. So the high affinity to different molecules.
And there's an ozone and an oxygen band in the visible, and in the thermal infrared there's an ozone band, and these are ones that people will look for in the spectra of these planets if telescopes like that get built in the future.
That's amazing. That's really cool. So the next question I'll ask you is: so what's your favourite planet?
What's my favourite planet? Oh God.
All of them.
I really don't like to choose, because one of my favourite things about planets is how diverse they are. But there are a few. So there was one that I really liked a few years ago, which has lost some of its novelty because there's always a new, things that are moving. But there's one that's called HD 80606.
I like the names that people make up for the planets.
So HD 80606 is the name of the star, and then B for the planet. But it was, and I think still is, the planet with the most eccentric orbit known. So it basically it's an incredibly elliptical orbit. So it goes out to almost the same distance as the Sun to Earth distance. But when it's at its closest approach, it's actually at 3% of that distance.
Oh wow! That's
so it goes from really, really hot to very cold. Now it's a gas giant planet. There's no way it's inhabitable. But the fact that it receives this kind of periodic boosts of heat makes it very interesting to study how heat is then redistributed into the atmosphere, and it transits across its parent star, and also the way it was found. So it was found by the radio velocity method, the Doppler method first, but then people found that it. So people said, okay, it's got this very eccentric orbit. Let's look at how bright the system looks when around that what we call periastron, when the planet is close to the star. And then they said, it passes behind the star. Actually, they saw a little dip. And then they said, well, if it passes behind, then there must be a time just afterwards where it passes in front. Or there may be. And then so everybody then
jumped on it,
tried to see it, and actually the first people to see it were two different groups. One of them was a bunch of students at UCL who were using an old telescope from UCL as part of their master's project. So that was also really nice that they... and I was involved in some of the first analyses of some of these data. But it's no longer flavour of the month, because that was at least 5 years ago or more. But it was a really nice system. I really like... There's one of the planets discovered by the MERF project recently, so it's orbiting an M star. I have forgotten its little telephone number. It's LHS something. But it's one of the most promising for atmospheric characterization that's been discovered recently. So that's going to be a really, really cool.
It's really amazing. I always read on different science magazines or stuff on Facebook about science. They're all finding all different kinds of planets. And I found one which is quite interesting, where one of the planets I saw was so dark that it absorbed almost 99% of the light, and so it didn't emit any light. And so if you were on that planet, you wouldn't. It was darker than coal. It was so black that you wouldn't be able to. If you know any, that you have that one. I mean,
I don't know which one it was specifically, but it's true that observations of hot Jupiters. So these are planets like Jupiter, very close to their host star. They're the easiest to observe planets because they're big and they're close to the star. But for many of them, people tried to measure the albedo of the planet, so how much light it reflects, by looking at what happens when the planet goes behind a star. So when the planet goes behind a star, its light disappears. Okay, and if you're looking in the infrared, what disappears is the thermal emission from the planet. But if you're looking in the visible, then what disappears is the reflected light. And people who model these planets had been predicting for a long time that they would have very low albedos, that there wouldn't be much reflecting light. Then people started to think, well, maybe these planets have clouds, actually, and the clouds would reflect quite a lot. But the fact is, when you try and make the measurement of the light disappearing in the visible, it's not been done for many planets.
Okay.
But for many of them, we only have upper limits, which means that they have to be very dark.
Oh, I see.
Okay. I actually had a PhD student here a few years ago who was involved with the first positive measurement of this kind, where we actually saw something.
Yeah.
And it was a planet that was cloudy.
Okay.
So that may well be why we saw something.
Okay.
But for some planets, we now have very strong constraints that say they almost reflect no light in the visible. That's true. But that doesn't mean they emit no light. Because all the light that they receive, they must remit at some point. Otherwise, they just get hotter and hotter and hotter until they explode, basically. So they probably do emit, but in the infrared.
Oh, I see. Okay.
And so I guess if you were a creature living on that planet...
Yeah, you'd be badass, first of all, because you extreme.
Well, they're extremely hot.
Yeah.
But you would, basically, you would feel the radiation coming from
get cooked,
from the planet. Yeah.
That's amazing. Now I've been reading a lot of research recently on Cassini, and it's doing its dive back into Saturn. Do you have any specifics on some of the inner planets in the solar system, or is it mostly exoplanets that you?
I mostly work on exoplanets. You can try me on a few questions, but I don't know that much.
So Cassini is basically going in for its next dive through the rings of Saturn. I think its final mission is in the next 3 months to just go into Saturn.
That's right. It's going to get as close as it can.
Now, what do you think some of the findings are going to be for that? Do you think?
Well, I think I've heard of a few things. I'm going to stay very vague because it's really not my area of specialty. I think the structure of the rings of Saturn is sculpted by Saturn itself and its moons and all the satellites of Saturn. So by going through the rings and sampling the composition and the structure of the rings, they understand better all the different gravitational interactions between all the components in the Saturn system. And then by getting as close to Saturn as possible, first of all, they get more detailed images and spectra of Saturn, so they get to tell what is in its atmosphere in the various different places. There's also, I believe, some open questions about what's called the gravitational moments of Saturn. So basically, the just how perfectly spherical it is.
Okay.
And also how its density changes as you go inside the planet.
Interesting.
And by flying close to it, you can probe that. So basically, you look at how the gravitational field changes as you get closer and move around it, and that tells you something about the internal structure of the planet. I won't go into any more detail than that because I would be starting to sort of waffle.
Okay, that's fine. That's really cool. And I think when people when scientists make these kinds of amazing telescopes and amazing spacecraft, they can probe deeply into it. It's an astonishing thing. I think humans can do that kind of thing. I think of Voyager 1 and 2 and think how far that gone, launched in the 70s, and it's crazy how far we're going, and yet we still have so far to go. Have you done any work on Alpha Centauri system at all?
I have done work on Alpha Centauri. So with one of my students, we looked at, so in 2012 there was a paper published reporting the detection of a planet with a mass similar to the Earth in orbit around Alpha Centauri B, so Alpha Centauri A and B are two stars. Alpha Centauri A is quite similar to the Sun, Alpha Centauri B is just a little bit smaller. They orbit each other but in a wide orbit. So most of the time you can look at just one star without seeing the other one in the same bit of your telescope. And so astronomers had been monitoring for several years Alpha Centauri B, and they found that its radial velocity, its Doppler velocity, changed. Now most of those changes were due to two things. First of all, the orbit of the binary, and then the fact that the star has star spots.
Really?
Just like the Sun has sunspots, most stars have. And that star doesn't particularly have lots of star spots. It had variable amounts of star spots, so different seasons they saw different amounts. But after filtering all that out, the authors of the study found that there was this signal with a period of 3.2 days that was easily explained by a sinusoidal variation, and they interpret that as a planet. with a period of 3.2 days.
Okay.
So nobody claimed it was an inhabitable planet, but it was interesting because it was very low mass. It was the smallest Doppler signal that had ever been reported, and because it was around Alpha Centauri b, which is one of the nearest stars to the Sun. And I had a student who was working on trying to develop more sophisticated ways of filtering out the signal from star spots in radio velocities. It's one of the biggest problems we have. And initially we just tried to reproduce what the authors of that study had done, and we found similar results using our own method. But I always had a little bit of a suspicion that that result might not be reliable.
Okay.
And one of the reasons was that if you look at the times when all the observations were made, you find that that sequence of times had power at 3.2 days.
Okay.
So it basically means that if you imagine observing something that was just constantly increasing by exactly the same times as they observed the system, you would then be able to reproduce the data partly using a sinusoid at that period.
Okay.
And so that wasn't the dominant component, but once you do all the other sophisticated analysis that had to be done in order to remove the binary, the star spots, then that signal got boosted basically by all the subsequent analysis. And so we were able to show, so I had this inkling, but that was just an inkling, but my student, using very detailed simulations, was able to show that the planet was in fact basically an artifact due to what we call the time sampling of the observations.
You say artifact, what do you mean by artifact?
But it wasn't there. There isn't one there.
Okay.
It doesn't exist.
Wow.
It's just an illusion, if you like, due to the time sampling of the observations. And so now we've continued working in that area, trying to look at how do you choose the times as best as you can to minimize the risk of such a thing happening. Okay. And also when you have a data set, how do you do all the tests that you need to do to make sure that any signal you have are real.
Okay, so it's just about the methodology and having it as precise as possible.
But the thing that was weird is that, so people, there are very well established protocols for how to define whether a signal is statistically significant, and if you apply all those tests naively, you would have said the planet was real.
Yeah.
It's sometimes it's basically because whatever the best model we do for the data, it's never going to be perfect. Okay. And so that's the reason why you can get counterintuitive results, even if you follow all the nominal rules for how you should analyze data.
Oh, interesting.
So it's a little bit arcane. But, so it was, at the time, we were a little bit hesitant about publishing because that planet had been such a big splash. Yeah. And we hate to be a killjoy. But we had some, very friendly discussions with the author of the initial paper, and he agreed with us, and so that gave us the...
Well, that's good though, I mean, it's always better to, find the true answer than it is on a false hope, because say if you want to do a mission on it, for example, and
of course,
you go there, or do some observation and it's not there, then you've just wasted a lot of your investment and time.
Well, talking about mission, so there's an even more nearby planet, which is Proxima Centauri.
Yeah, Proxima.
So that one, I think the planet is real. I don't have any suspicions about it, and that is in I think an 11-day orbit around Proxima Centauri, and because Proxima Centauri is a low mass star, that's actually in the habitable zone. Wow. Now the planet doesn't transit, so we don't know its true mass. Okay. And
why does the planet not transit?
Well, because it only transits if the orbit is inclined just the right way, as seen by us. I see. Okay. But it's still an interesting system. Wow. And there are, there's this, I don't know if you've heard of it, but there is this thing called the Breakthrough Initiative. So Yuri Milner, who's a oligarch in the United States, has teamed up with Stephen Hawking to and put a large amount of money, I can't remember, but it's in the tens or hundreds of millions of dollars, towards funding research that could lead to sending a spacecraft, not a manned spacecraft, but sending a spacecraft to Proxima Centauri. And they actually started this before the planet was discovered, but of course it gives them a big boost that the planet was discovered. Yeah.
But how would one go about doing that though? Because if it's, I think it's 4.2 light years away roughly, so it would take a very, very long time to get there. What would be the best method to get there as quickly as possible?
So this is really outside my area of expertise, but I understand that what they're considering is something with a solar sail, so that it's radiation pressure from the sun that carries it away, and to make it extremely light and tiny. So what they're thinking of sending is just a tiny, maybe even a centimeter cubed type thing, just enough to send very basic information back to Earth, with a huge sail to collect all the radiation pressure from all the
cool. So basically the way we've been doing it here on the ocean, except in space.
In a way, yeah, in a way. But that being said, I don't believe that they have in any way a proven technology that works. Right? It's very, very
early days. Yeah. Okay. Oh, that's amazing. So when you look at the when the James Webb Telescope first goes out, how is it exactly allocated? Who gets to choose?
Oh gosh,
how does it work?
That's a big gunfight. No, so it's actually very organised. So first of all, there are teams that have invested a lot of time in designing and building the instruments that will go on James Webb. Plus, there is also the team that developed James Webb itself. Okay. And all of these teams have what we call guaranteed time observations. So they've been allocated a certain number of hours of the time on James Webb to do with what they want. And they've spent years developing science experiments that they want to do with that time. And then in the first 6 months of James Webb, there will also be what we call some early release science observations. So basically these are programs that will be proposed by specific people for specific goals, but they should be intended to test all the different modes of operation of the instruments as well. And the data will be taken and released immediately to the whole community, and it's there to help then people prepare further proposals for the future.
I see, that makes sense.
Yeah, and then after that, basically there'll be a call for proposals every year. People will respond saying, well, I want to do this with this instrument, and it will take me this much time, and this is cool because blah. And then there'll be a panel that reviews all these proposals and ranks them and allocates time, and they will try to balance lots of
like a committee essentially.
Yeah.
Okay. Oh wow.
And it's a similar procedure that already takes place for Hubble and for many ground-based telescopes, but because James Webb is so powerful, especially in the first few years, there'll be immense competition.
Everyone's like, give me the telescope, I want to use it.
And so there will also be quite a lot of people trying to get together, and rather than 10 people competing with 10 different proposals, people trying to submit a joined up proposal, probably, because it makes more sense.
Now I want to speak to you about the Large Array Telescope, I believe, is that what it's called? Basically it's a radio telescope.
Do you mean the SKA, the Square Kilometre Array?
Yes, Square, that's the one, sorry, yeah.
There's lots of people here in this department who work on that.
Really?
I'm not very knowledgeable about it. I can tell you a few things perhaps, but...
So I think at the moment it's in, correct me if I'm wrong here, but it's currently in production, where they're using it across different countries.
So they are... I believe there are SKA precursors that are in operation, so instruments which in their own right are very powerful radio telescopes, but they are there also to teach us about how SKA might work, and there's a lot of challenges with operating the SKA that people are using these precursors to learn from. And I believe the building of the SKA itself is starting. So there will be, part of it will be in South Africa and part of it will be in Australia. The core of it will be, I think, in South Africa. I don't want to say something wrong. But so it won't be online for quite a few years still, but it's a huge project with
so
lots and lots.
Would you be able to use that to maybe help you find specific properties of planets at all?
So there is definitely one area of interest, which is that if you have a planet with a magnetic field, the magnetic field of the planet will interact with the magnetic field of the star. So for example, the Earth has a magnetic field, and this magnetic field essentially shields the Earth's atmosphere from radiation from the sun and from cosmic rays. And that's one of the reasons, one of the ways that the atmosphere is protected, otherwise it would be evaporating away.
And it would just be extinguished.
Yeah, and also otherwise there would be much more harmful radiation reaching the ground and reaching life on the surface of the planet. Now, if you take a planet and you put it much closer to the star, then it will start, its magnetic field, particularly if that field is stronger than the Earth, will start interacting very violently with the star, and we have an analogue to that in the solar system. So Jupiter and Io both have strong magnetic field, they're close together. Io is one of the moons of Jupiter, and as Io rotates through the magnetic field of Jupiter, it emits, radio waves are emitted. And you can imagine something similar with a star and a hot Jupiter planet. with its own magnetic field. And people have calculated what sort of radio emissions we would see. It would be very low frequency, but it would be in the range that SKA might see. And even some of the precursors to SKA, like LOFAR. So that's definitely an area. It's not one that I've looked into personally, but I know that people are interested in doing that.
Okay, nice. So how did this all begin? How did you start your career into this? At what point did you think, okay, I'm going to grow up and be basically a planet hunter and just search for planets?
So I always liked science, but I wasn't sort of restricted in which area of science I was interested in until quite late. When I was thinking of which degree to study, I actually wanted, this is going to sound weird, I wanted to be a sound engineer for cinema.
That's pretty cool.
Because I liked cinema a lot.
Yeah.
But I knew I wasn't going to be an actress or and I have no skill for photography. So there were people around me who were involved in manipulating sound and images, and I thought that was quite interesting. But somebody who worked in the field told me technology is evolving really, really fast. It would be an advantage to have a physics degree so you can understand the technology.
Okay.
Which was good advice in the sense that I think everybody would benefit from doing a physics degree.
Definitely.
But I suspect I was bribed by my parents to say that. Nonetheless, I think in a sense it's always a good idea to do a degree in something a bit fundamental for your first degree, and then you can always specialise later. But then basically while I was doing my degree in the summer, I took summer jobs in various places. I did one in a molecular biology lab, and I did one in the Institute of Astronomy in Cambridge, and I enjoyed that. And I actually, in a way, many astronomers wanted to be astronomers since they were little because they loved looking at the star and they were fascinated. I did find it fascinating, but what made me really want to do it was the practice of it. And the practice is not as glamorous as you think. It's basically sitting at a computer writing programs to analyze data. But I really loved that. And so that is when I decided, okay, I really want to do this, and I forgot about sound engineering. Although, I mean, I think there's lots of different areas of science where I would enjoy working. Astronomy is just the one that I happened to come across. And then I spent, before my PhD, after my degree, I spent 6 months working at the European Space Agency. They have
amazing.
They have a young graduate trainee program that you can apply for, and so that was really nice. And I worked then on a proposed spacecraft to look for transits that was called Eddington. That never flew, but actually its successor, a sort of proposal that emerged from that called Plato, has been selected by ESA and will fly in 2024. So I'm still working on Plato today.
Awesome.
And then I basically applied for a PhD and did a PhD and kept working in this area. So that tells you how.
That's awesome.
Yeah.
What was it like working at a European Space Agency? What kind of was it? Is it all as glamorous as you think it is? Because I mean, in my mind, like doing this kind of research and stuff is always kind of the cutting edge of it. Like, you know.
Well, there's a huge diversity of people who work at the European Space Agency, right? So I was in their space science division. So actually, the people working there are mostly astronomers, just like you would find in a university. Many of the people with permanent positions there are responsible for the scientific management of one or more of the space missions. The science space missions that ESA runs. So for example, the guy who was my boss then was, at the time, project scientist for this Eddington project. And then as you get more senior, there are people there who are then managing the whole science program of ESA. But there's also engineers who develop cooling systems, who model the spacecraft communication technologies, all sorts of things. There were people down the corridor who were working on the space station astronaut program. I had a friend that I used to have lunch with whose job it was to make timetables for the astronauts and what they would do every day. And I tell you what, it did not make being an astronaut sound very pleasant. Their timetable is preset to every 10 minutes. Everything they do is defined by 10-minute intervals.
Well, that kind of makes sense. I mean,
their time is so precious, right?
Exactly. I mean, you're in an environment which is extremely harsh, just floating around in like the void of space, circling the Earth. I mean, that's
no. I mean, it's kind of fascinating, but it's also quite an eye opener.
No, definitely.
At the time. Wow. So it is glamorous in many ways, and not in others. I mean, there's also a lot of anything to do with space involves quite a lot of it's a bit harsh to call it bureaucracy, but there is a lot of bureaucracy, but also a lot of just very, very careful record keeping and making sure that everything passes every test 10 times over, because mistakes are so costly.
Definitely.
So if you compare, doing astronomy with space missions, it takes a lot longer to get from the first idea to the result than what you can do on a ground-based instrument.
Okay. Wow. So I want to ask you a bit of a weird question. So, what do you think the odds are that extraterrestrial life exists in all different kinds of planets?
So I think the odds that extraterrestrial life exists are pretty high, simply based on the fact that it appears that planets are very common, and increasingly it appears that planets broadly similar to the Earth might not be quite so rare. Where I interpret broadly is very broadly, they're just within a range of a factor of few in size and in insulation. And then the other element that makes me say this is that on Earth, life, very primitive life, emerged very quickly.
Okay.
The first signs of life we have on Earth are almost as old as the oldest rocks that we have. So that's a sample of one, but it suggests that it might not have been so difficult for life to emerge. Now, I wouldn't be so ready to bet on complex life, simply because it took a very long time to emerge on Earth. But again, it's a sample of one, who knows. The other thing is that life, so one big question is how common is life that we might be able to detect?
Yeah.
Because for a long time there was life on Earth, but it would have been extremely hard to tell from the outside that there was.
That makes sense, yeah.
And that is a very good question. It all depends, a lot of it depends on how long it takes for life to develop to the extent that it affects the atmosphere of the planet significantly. Basically, that's what we can easily detect. Compared to how long the conditions remain propitious for life.
Yeah, that makes sense.
And that must vary from star to star, but it's a big open question. Even we still don't know exactly how life emerged on Earth, and we still don't know how easy it is. One of the nice things about that sort of experiment is if at the moment we're looking for it, we're looking for it in a tiny sample of our galaxy, right? Because that's all we can. If we found it, we would immediately know it had to be extremely common, because we're looking in just such a small bubble. So that would be quite cool. The nice thing is we live at a time where it's actually completely realistic to say, let's look for it and we might find it, right? So there's no, to my knowledge, there is no fundamental technological limitation. There are limitations of cost, but they're not insane. Things are expensive, but they're not insane. There's no scientific limitation. We can do it. So it's really quite exciting.
That's amazing. I recently watched on Horizon on BBC, one of the guys...
quickly check the time because...
Sure.
Yeah, I have to go.
That's fine, not to worry.
Okay.
But anyway, I'm sure we can do another podcast at some point if you're interested again.
I mean, if you want to, there are people around who might be able to, for example, if you wanted to do one on SK, I'm sure there'll be people you could talk to. And there's people here also who work on Cassini, for example. If you wanted to do a Cassini related one,
that'd be awesome.
To time with the flyby.
That'd be great. That'd be amazing.
Yeah, well, I can. I'll send you in an email the email address of somebody I know who works on Cassini.
Well, thank you very much for your time, Susan. And it was really enjoyed this. I can keep talking to you about this all day.
Yeah, me too. But I have a visitor today.
No, that's okay. Don't worry. That's fine. Well, thank you very much for your time anyway.
Okay, great. Nice to meet you.
You too.
And, okay. I'm just gonna.
Hi everyone. How's it going? I really hope you guys enjoyed today's podcast. I sure did. If you liked today's content, then please hit that like and subscribe button down below. If you didn't, then hit it anyway. I hope you guys have a good day, and I'll see you guys next time. Goodbye.